Now let's look at the impedance of a capacitor. So here's our symbol for the capacitor in the time domain with an instantaneous current and instantaneous voltage shown for the passive sign convention. Both the voltage and current will be sinusoids here. And we're going to start with the voltage, where we have a peak value of V sub m times the cosine of omega t plus phi. And in using Euler's notation, we'll write that as V max times the real part of e to the j omega t times e to the j phi. And then we apply our definition of the VI relationship between voltage and current for a capacitor. Current is capacitance times the time rate of change of voltage. And if we take the derivative of our Euler's function of voltage on the capacitor, well, the derivative of e to the j omega t is j omega e to the j omega t, and of course e to the j phi itself is a constant. So our phasor current looks like j omega c times V max, the peak value, times e to the j phi. We already know how to do the phasor voltage because all we have to do there is remove the restriction that we're only taking the real part of the time varying function, V, and also setting t equal to 0. So the phasor voltage just became this simple V max e to the j phi. Now the definition of impedance here will be the voltage phasor divided by the current phasor. And when we put those together, then we get V max e to the j phi in the numerator and j omega c V max e to the j phi in the denominator. Now the e to the j phi's cancel, the VM's cancel, and we're left with 1 over j omega c. That becomes the same as minus j over omega c. Remember, when you take 1 over j, that's the same as minus j in the numerator. Let's calculate the impedance of a capacitor. F, the frequency, will be 1,000 hertz in this example. Here we are with our phasor definition or designation of this capacitor with phasor currents and voltages in the passive sign convention. And we take the capacitance at 200 microfarads and get our radian frequency of 2 pi radians per cycle times 1,000 cycles per second, and that's 6,283 radians per second. And Z then is 1 over j omega c, and that's going to turn out to be minus j 1.257 ohms for that particular capacitor. And if we take another example, let's go up to 20 kilohertz for this one, and let's see the 50 nanofarads, and our frequency then is 2 pi radians per cycle times 20,000 cycles in a second, and that'll equal 125.6 thousandths of radians per second, or kiloradians per second. Now Z is 1 over j omega c again. So if we have 125.6 times 10 to the 3 radians per second and 50 times 10 to the minus 9 farads, that's minus j 159.2 ohms of capacitive impedance. If we look at the phasor diagram for the VI relationship of those for that capacitor, we would always see a 90-degree difference between the current and the voltage. However, in this case, as the case with all capacitors, the current will be leading the voltage by 90 degrees. So it's out in front. Remember, they're spinning counterclockwise around the origin of the complex plane. We started out with phi leading or ahead of the real axis by phi radians or degrees, and the current that follows will be 90 degrees out in front.